welcome everyone. So it's my pleasure to welcome Michael Small from the University of Western Australia. We'll be talking about learning the dynamics from radial basis functions to reservoir computers. Thank you.
Okay, thank you. Thank you for the invitation to speak here, and thank you all for joining me. What I'm going to talk about, actually, I've got kind of an easy task and also kind of a hard task, because most of what I'm talking about is either work that was started a long time ago by my PhD supervisor and his supervisor, and Alistair Mees is in the audience there somewhere listening to this. So I'm going to be trying to explain radial basis functions and minimum description length to you, Alistair. And a lot of the other work that follows on from this is more recent stuff that we've been doing in Perth in the area of reservoir computing, which is work that Thomas Jungling, who's also on the call here, started us on that journey. And so first off, the work that I'm presenting here, there's a whole bunch of people that contributed to it that aren't me. Most of these people either came up with the ideas or did all the hard work of creating all this stuff. So I'm just here presenting the fruits of all that labor. So I guess the place that I want to start is why, if we're interested in dynamical systems, do we care about models in the first place? And what is the context that we want to even look at models as dynamical systems? And so the usual way we think about models, and this is probably revision and probably familiar to all of you, but the way that we think about models from dynamical systems point of view, if we have access to time series of observations, then we want the model that tells us something about what the next time series observation is. So of course, underlying these time series observations, there's a dynamical system that's generating them. There's some observation function that's spitting out the ZT, which are scalar observations through time. And we want to, in some sense, predict the next observation. And of course, the standard way in which we do this is with some version of embedding. There's lots of complications in embedding theory around how to do this correctly, how to choose the appropriate dimension D and even lags T to get a good embedding of the system. I'm going to kind of assume that's all happened, and we've figured out how far in the past we have to look. So we've got ZT minus 1 to ZT minus D to predict the next observation. And if you look at almost 80% of the stuff in terms of modeling dynamics from time series, the way in which you evaluate the performance of your model is how good your predictions are, which is kind of obvious, right? Except what we really want is not just a prediction that gives us a small error, but a prediction which is in some way useful. And in engineering recently, the term digital twin has come into vogue as a way of describing this kind of process where you have some duplicate of your underlying system, which you can manipulate and test on. But this digital twin is not much more than a model. But the point is that the purpose of the model is not just to make short-term predictions, but because the model gives you access to the properties of the underlying system. And in dynamical systems theory, of course, we think about this in terms of the evolution of the model dynamics producing something which looks like the original dynamics of the true system. So very simple example of this. If I take a nice simple chaotic map, which is shown on the left there, it's a two-dimensional map, so it's xt and yt. If I just have access to the time series xt on the right, and I wish to model the dynamics from that time series, well, I can take a short section of the time series, which is shown here on the left in the true one is the blue line, which is underneath the predicted red line, and there's an error as a green line. So I've built a model from a short section of data, and I can make my predictions one step into a future, or I can make my predictions iteratively, which is what I really care about if I want to measure the dynamics. So the one-step predictions on the left look really good. The error is quite small. Model's built from not much data. But if I try to iterate those predictions, I get something which doesn't look anything like the original attractor, right? So if I take the predictions and iterate them out, I get, in the delaying coordinate system, the red object here, which looks nothing like the blue object. Of course, that's because this is a bad model. if I have a good model, then I get much better predictions. And my dynamics of my model look like the dynamics of the underlying system, which I care about. And then I can have some confidence that looking at properties of the model, dynamical properties of the model tell me something about dynamical properties of the system underlying that model. And the thing to notice here, of course, is that I go from a pretty bad looking model of the dynamics to a very good looking model of the dynamics, and yet my short-term prediction has hardly changed. My one-step errors are small in both cases. And as an aside, this one is kind of interesting because actually the short-term, the predicted model on the right, although it's a bad model of the dynamics, it has got some of the interesting features of the dynamics. So it is actually chaotic. It is actually got some sort of complicated behavior. And one of the ways, this is a plug for some really recent work we've just done, one of the ways you might try to quantify how good the prediction is to look at something like correlation dimension. And here it would be perhaps hard to tell the model prediction in the red-orange color from the noisy data in blue just by looking at correlation dimension because they're similar kind of structural complexity. But if you want to look at measuring how good you're matching the attractor, you really want to look at the total structure of that. And so one of my students, who I haven't seen online here, but he's somewhere hiding there, has looked at doing this using something called persistent homology, where you actually try to measure the structural properties of the attractor and quantify it that way. But anyway, the point for the time being is simply that we want to model the dynamics, not just the short-term prediction error. And so this is work that I started working on under Alistair and Kevin's instruction way back in the end of the last millennium for part of my PhD. And it's informed kind of the way that I've looked at machine learning since then. And I view the machine learning problems that we can see as simply an exercise in curve fitting or surface fitting. So if you think back to the embedding approach, I'm taking some sequence of past observations to try to predict the next observation. Well, that's just a function from Rn to R. So I'm just trying to fit my data, which exists in that Rn plus 1 dimensions, to get a surface that goes through that, and that is my dynamics. And I've lost focus here. There. Okay. Okay, so we can take the data, we can put the data in a matrix. So my observations now exist in a matrix, and I construct a vector, which is my prediction of my next state. And I'm interested in, first of all, minimizing the error, but also then capturing the dynamics. So it turns out that we still need to try to minimize something, and the easiest thing to minimize is the error. Just as an aside, in the notation here, I'm using Julia language notation. So f is a scalar function applied to the rows of the vector here. So you get like for each row, you get an evaluation of the function, and you're just mapping that across, differencing that from the next true state. Okay, so very simple. We've got a model of some form. We want to take our functional approximation exercise is just taking rows of that model to get them to be as close as possible to the output states. And we're minimizing error. And this is hardly a new field. And so even when I came to it in the late 90s, it was been about for a long time already. And the tools that I was using was radial basis function modeling and applying the idea from Kevin and Alistair of minimum description length to try to quantify the goodness of fit of a model. So the basic idea, okay, so first of all, radial basis model is a kind of neat view of functional approximation because you're simply taking your observations, your xi's, and you're constructing a set of basis functions. They are the phi j's. Each of the phi j's is an evaluation of your data in your state space, but the evaluation is localized about some point Cj. So the radial nature of this means that each of these functions, each of these phi j's is restricted in domain to be about some location, some center. These phi's are decreasing functions, and the extent of it is dictated by the denominator here. So typically phi j you could think of as Gaussian or something like that. The implementation I'm using is slightly more generalized than that, but you've got some decreasing function. Each of these phi j's is localized about a center, the Cj, the location where you are measuring from, and restricted via radius rj. Choosing the structure of your basis functions, your phi j's, choosing the location cj's, and choosing the radius rj's, that's all nonlinear. But having chosen all those things, then it becomes a simple linear exercise to choose the weights, the lambda j's. So you can think of the phi j and everything in the bracket as a nonlinear transformation of your data matrix, the X, and then we're just doing a least mean squares fit over the columns or rows, depending on which way you're looking at, of that matrix. All of this is fine. This is well and good. This is well established, straightforward stuff. The question that remains is, how many such basis functions do you want? So that's the K in this equation. Recently, there's a whole bunch of regularization methods which people are using in reservoir computing. We'll use them later on. This is kind of a bit of a dinosaur of a method, but still works and does a fantastic job, I think, of capturing the structural complexity of a model. And the basic idea of description length is what you're measuring, and I'll try to go through some of that formula. I realize it looks a little bit excessive in a moment, but the basic idea of description length is what you're doing is you're measuring the cost of transmitting your data, your time series, versus the cost of transmitting your model and the model prediction errors. So the idea is, if I've got a set of observations, my time series, and I build a model of them, if it's a good model, I would hope that that model provides a reduction in the complexity of the transmitted signal. So describing the model and the model prediction errors is, we hope, more compact than just describing the data, if it's a good model. Okay, so that turns out can be computed, and essentially we're just computing the encoding of all the parameters of the model to some precision. And the key thing out of all of this formula that makes description length useful and makes it work is that there's a term here, and it's the third term in this expression, the sum of the log delta j. What this term is each of the parameters in my model, we need to specify it to some precision to make the model work. And that precision depends on the Hessian of the function. To say that more simply, the precision of my parameters depends on how sensitively the model changes when I change that parameter. And that depends on the second derivative of the model with respect to those parameters, right? So all that sounds complicated. The expression doesn't look very neat, but it's all completely computable. I've got my model written down here on the top line. I can differentiate it twice, so I can work out the Hessian matrix. I can then, with a bit of effort, and there's a lot of heartache and complications in solving this Q delta equals 1 on delta, but it can be done. I can find the precision of each of those parameters. The rest of the terms in this expression, well, the first term is the cost of the model prediction errors, right? That's the log mean sum of square error. There's a correction term for the essentially the complexity of the chosen expression of the data strings. And then there's some correction terms for the length of the data. N is the number of data points, which I think I've changed my notation from earlier on that one. Okay, so basically the idea is I'm going to build a model of my data by putting down a bunch of basis functions. These are Gaussians. These exist in my embedding space. So I've got my time series. I embed my time series. That gives me points in a high dimensional space. I plonk down these Gaussians in that space, and I take some linear combination of them, and I stop making that bigger and bigger when description length tells me I've got the most compact model. And description length is essentially measuring the complexity of the parameters of those models. So it turns out,
Michael, can I ask, does minimum description length have some Bayesian justification?
Yeah, there's a Bayesian parallel to all of this. The way that I'm presenting it and the way that I'm thinking about it is purely as a coding theory exercise. But you can construct it in terms of some belief and some prior distribution on your data values, and the cost of the model is informing deviation on that.
Okay,
Does that make sense? Yeah. So yeah, I mean, all of this stuff. In fact, there's a nice book that I read that actually put all of description length into the Bayesian framework. But just the way that I've always thought about it is just as a coding exercise. But essentially, that coding exercise is the it's essentially doing gzip, right? And so that's building a model on the distribution of your data values. So there's a prior there which you're building up on. That makes sense? Okay, so we can do a lot of fun things with this, and we can build models. The model that I showed you earlier of the two-dimensional attractor and the nice attractor that we got out of that was built with exactly these techniques. One other thing we can do is we can actually throw out the basis functions as I've described them as Gaussians, and we can replace them with polynomial terms, right? So instead of these complicated basis functions that we have here, if we treat the data as not as an embedding, or even as an embedding, but as an embedding or not, as the independent variables of your system, and we could look at combinations of them. They are the different polynomial basis elements, and we could try and find a model in terms of those, right? And so stealing an idea that Reggie Brown published a couple of years earlier, this is exactly what we did here. So we're using a technique, which is what Reggie introduced, called Adams integration. Well, he introduced the application of Adams integration in this context. We're essentially trying to estimate the equations of the Lorentz system by taking the x, y, and z coordinates, the data, and trying to build a model of x dot, y dot, and z dot, right, using this description length principle. And so you've got all of the polynomial terms up to some order. Here, I think I'm using everything up to cubic. It was a long time ago. I think it was cubics we've been up to. And then we look at the terms that the model selects. So it turns out that, so for example, to build a model of x dot in the Lorentz system, you've got y and x, 10 times y minus x, which is what the Lorentz equations are. You've got some extra terms here. Minimum description length has not done a perfect job. It's overfitted a little bit. You've got these three extra terms, xz, yz, xy. The magnitude of them is quite small, so it's not terribly disturbing. And also, we're doing this on a short section of data from the Lorentz system, essentially on what today would be a pocket calculator or an iWatch or something. But if you look at the x component, the y component, the z component, description length has decided to build a model that includes all the necessary components that match the true equations, and a few extras. So it's overfitting a little bit. At the time, although I've never actually bothered to check this, I would speculate that some of those correction terms are actually introduced by the fact that I'm not fitting the data to the true x dot, y dot, z dot, but I'm fitting it to a numerical integration scheme. So there's small errors in that numerical integration scheme, which may well be reflected in these additional terms. But in terms of the currently in vogue idea of extracting equations from time series data, this is it. You can easily read off from here the true equations of the Lorentz system just by applying this kind of basis function idea plus Okay, that was embarrassing. Back again. I had my VPN switched on because I was getting the presentation from work, and it just suddenly quit on me. So let me just grab the presentation again and share. Okay, checking that I'm not muted. Yes, okay, good. So the basic idea here is that we're making iterated predictions, as you do if you just have a one-step model, but we would like to try to capture a direct prediction of the envelope of uncertainty moving forward. And so what we're doing by that is using essentially a linear interpolation scheme on those iterated predictions to produce the envelope of future states. And that's the solid lines that you see in each of these pictures. And you can see that the dotted line, which is the truth, the dashed line, which is one prediction, so it's a pretty noisy, poor prediction, but the envelope of uncertainty is doing what you kind of expect the Lorentz system to do. What I really want to talk about today, and rather than confusing things too much, is how we actually apply some of these ideas to real world data. So I didn't say at the beginning, but one of the things that I spend quite a bit of my time working on is we're running a industrial transformation training center. That's the Australian Research Council's name for it. But essentially what this means is we have a research center where the goal is to train PhD students to work with industry problems and industry data and try to develop PhD students into researchers that will work on real world problems. And so this particular center, the problems we're looking at are all in the area of maintenance. So in Western Australia, as I think most people have some idea, Western Australia is basically a mining state. We make most of our money out of digging stuff out of the ground, processing it a little bit, and then selling it overseas. So we have large operations with lots of large industrial components that are expensive to maintain, but they're also even more expensive if they have to take them offline to repair them. So the critical question for most of these operations is, how do I maintain this equipment with the minimum possible downtime? And so what we're doing with these mining companies is to try to apply, well, we told them it was data science techniques, machine learning, dynamical systems, complex systems, Bayesian statistics, a whole bunch of different theories are being applied to try to make better predictions of when their equipment is likely to fail and how to maintain it. So one very simple example of this is, I'll skip forward over that, is this data here. So this is actually discharge of a series of batteries. So what you're looking at here is a whole bunch of different recordings of data from a real system. So there's multiple recordings of the system, and the normal operation you can see down here is in log terms between -8 and -0.6. And each of these at some point fails and eventually reaches a critical failure at the threshold at the top. Obviously, there's a sudden jump discontinuity, there's a degradation in the performance. They would like to be able to predict when that jump discontinuity is about to happen. So, of course, my favorite tool, dynamical systems, building models of time series. I see this as a time series, and I want to try to predict when this transition occurs. This transition looks like a tipping point or hysteresis or some sort of transition or loss of stability of a stable focus. And I want to try to apply the machine learning radial basis function techniques to detect that change in stability. So first thing I do is I identify the obvious change. So now, again, there's multiple recordings here. The blue lines are the normal operation, and each of these blue lines stops at some point, and then there's a corresponding red line in the failure regime. So what we've done is, this is just one example. So the regular operation here on the left, you can see the pointer. Is that visible? Yep. So the regular operation in the blue here, at some point, critical failure, or critical transition, and later on, what they call failure when essentially the battery becomes useless. But already at this point, this is when your iPhone is now only lasting for half an hour rather than all day. So what we want to do is predict this upcoming transition before it occurs. So what we do is we build a model on the early part of the data, and we use that model to make predictions moving forward. And we look at how well those predictions predict the future. If the underlying dynamics changes, then one might suppose, not certain, but one might suppose that the prediction error is going to increase. Right. So what I'm plotting on the right here is and I think I've got ignore the key, that's actually incorrect. The top line here is the truth. The blue line is my one step ahead prediction, right? And the green is my error. So obviously, no, I say obviously, it's obvious, I think, my model is predicting a stable focus pretty close to 0. And that's the data wandering around the stable fixed point. And once the true signal jumps off away from that fixed point, my error becomes large. So predicting failure at this point is not the issue. The issue is, if I look in this window just before failure, you will see that the prediction error starts to increase. Right? So above about time step 300, before you get to about 350, you can see the error starting to grow. It grows larger at some places in the past, but it starts to grow. But this is where the stability of the fixed point decreases, the error increases, and eventually it becomes unstable and falls off. Okay, so we can apply the same principle to each of the data sets. However, what we really want to do is have a universal model, in the sense of a model that works for all of the batteries. And so so this is just a blow up of the same thing. So you can see the big failure occurs here, but if I look at the error, there's an increase in the error, and this is just showing it squared, but there's an increase in the error leading up to that failure. And you could perhaps predict even further back. I won't show you that because I think the idea of a hysteresis and tipping point should be familiar to most people in the room at the moment. But essentially what we're talking about is I've got a stable focus, which is becoming less and less stable until I get to a point where my stable focus shifts down to somewhere else. And I'm predicting that I'm using my model, which I've built on the more stable part, seeing that its error is increasing to predict the loss of stability as I get to the critical point there. But we want a single model to work on all of these systems, because we don't have the capacity to build a new model for each battery. We want to have a model of the batteries. And so what I'm depicting here is how well each of the models built on the data can predict the failure of that data set. What I'm showing you here is how well each of those models built on the data set predicts the failure of the other data sets. So there's 25 different data sets. Horizontal axis is the data set I've used to build the model. And the vertical axis is the data set I've used to build the model. The horizontal axis is the data set I'm making the prediction on. Right. So I'm computing the cross predictability on it, and essentially if a redder, yellower color is a high level of predictability. So the optimum, of course, we would expect to be the diagonal here, right? So that's when a model is being used to predict on itself. So if we were in the situation where each of the models was different from every one of the other models, we would only see a diagonal in dark red, and everything else would be yellow through purple. It turns out that there's only one single battery that doesn't work as well as the models built on themselves. So the takeaway message from this is actually not only can we predict the incipient failure of the batteries, but the models that we're building between them are translatable. So that is, the fixed point's pretty much in the same place, and any of the models is equally good. So
can I ask, Michael, is there electrochemical reason for expecting this bistability?
For expecting, I have no idea. I assume there is. I know nothing about that, to be honest.
That's okay. It'd be interesting.
Yeah, I was passed the data because a statistician colleague had applied some Bayesian methods to try to do the same thing, looking at the difference in the distribution, and so I was just doing the same thing with my equivalent modeling techniques.
You see, it could be that you've discovered something they didn't know about, and obviously it's important.
Well, I mean, what you mean, the fact that the models are translatable from one to another, or the bistability?
No, that it's probably a bistability, right? Because so it's clear they know about this relatively rapid transition to a poorer performance, but the fact that the model that you're generating is suggesting that there is already the poor performance
in the lead up to it,
pre-existing.
Yeah, I mean, I don't know much. I didn't actually pursue that, to be honest. I kind of assumed from my very sketchy high school chemistry that it was one of those processes which was a classic kind of tipping point situation. But I don't know. It's a good question.
They talk about I can't now remember what the words are, but anyway, they talk about the lithium or whatever forming a coating which makes it not work better. But you see, that wouldn't actually, to my mind, be compatible with bistability. Anyway.
Yeah. Anyway, yeah. So the point that I want to make with this data for the current talk, at least, is that we're not just playing around with models on the usual suspects, building models in the Lorentz system. Extracting the equation of the Lorentz system is nice, but we're interested in trying to get features out of the model that in terms of dynamics, that tell us something about the underlying system, which I guess gets to your question. Okay, so that was kind of the ancient, well, the battery stuff was fairly new, but the radial basis modeling description and stuff was kind of the ancient history part of the talk. More recently, we've been working on using reservoir computing, and I see a lot of parallels, and Thomas Jungling, who's on the call, often disagrees with me on this, but I see a lot of parallels between the ideas of reservoir computing as just a mechanism for generating lots of patterns from which you can choose the good patterns, and the way in which radial basis functions work, in that with radial basis functions, albeit you're selecting the basis functions that perform best, but you're selecting basis functions on the basis, sorry for the pun, on the basis of them generating lots of different patterns. So the basic idea, well, let me say, my version of the basic idea behind reservoir computing is that you have some network. It's recurrent in the sense that you've got connections between the nodes that create loops. This is important because this is where, in terms of the dynamics of the system, you're going to create memory. So you've got some recurrent network, you drive it on the diagram here from the left with some drive signal UN. That drive signal is placed in on some or all of the nodes, depending on how you construct it, and then you move forward in time. So over time, that drive signal from the past still persists in the reservoir as an attenuated echo of itself. And if you think of a very simple version of this, if you just had a ring in the reservoir, then if you just fed in x of t as your UN at one point and just watched it propagate back through that ring, this is performing exactly what a delay embedding is doing. It's creating a copy of the signal and its prehistory. Obviously, the reservoir does a bit more than that. The nodes in the reservoir have some nonlinear activation function, and they propagate that signal in combination. But the basic idea is that they have memory, and the signal that you fed in the past persists for some time in the reservoir. But the key feature of computational implementation of reservoir computers is that we don't optimize that recurrent network. It's randomly chosen in some clever ways, which Thomas and Thomas number 2, who's in the crowd, or Thomas number 3, who's in the crowd somewhere, have spent some time looking at. But we don't tweak the parameters, right? There's no tuning involved of the parameters of the connection parameters of the reservoir. All we fit is the output layer. And so the output layer is a linear transformation of the states of the nodes, which we're fitting to some desired target. Okay, so you've got a reservoir, dynamics moving about in these nodes that are connected in some recurrent way. You're feeding these in with some input signal, and then you've applied regularization and you've created an output on the other side of that from the states of those nodes. So in terms of fitting, in terms of the computational effort of what you're doing to train a reservoir, it's linear. The dynamics in the reservoir itself is nonlinear, and you gain some computational advantage because performing those, and this is an expression of what's going on in the reservoir, you gain some computational advantage because you can have a fairly large reservoir with a large number of nodes, and if you've chosen things correctly, generating a lot of patterns, and your output layer is just picking off the best of those patterns. And in a way, this is no different, at least at a conceptual level, from doing a delay embedding, constructing a large dictionary of basis functions, and then choosing the ones that represent your system well. Right, so it's a way of generating lots of patterns from which we can build a predictive model. So here in this equation is expressing that idea. Xi is the state of a single node I. There's a weight matrix, Wij, which is the connection between the nodes. Yeah, question.
Yeah, sorry, can I ask, so the reservoir is going to produce a memory of the input function, but in general, it's going to have infinite length, unless it's all working in discrete time, I guess, is that?
So the reservoir computation is a discrete time step.
Okay.
But and there will be attenuation of that, the memory of that signal, because it's being propagated here through this tan h to the hyperbolic tangent function. So eventually, the more distant signal just disappears. And one of the things that Thomas have spent a lot of time measuring is essentially the memory of a reservoir and how to construct reservoirs that have good memory properties. So a lot of the work in the reservoir community is to try to create reservoirs that have both good memory properties, but also good innovation. And so they drive the reservoirs themselves to exist in the regime close to the edge of chaos. So you've got as much memory as possible, but also as much novelty and interesting stuff going on.
Yeah, thanks. No, I raised it because you may remember there was this old paper by Broomhead and others pointing out that if you, for example, if you just put the input through a linear filter, then you can get failures in embedding. So they were emphasizing that you really need the finite, the bounded memory, right? Yep. So I was wondering if that's an issue. But anyway, if you say that tuning the memory properties is an essential part, then I understand. Yeah.
Yeah. So yeah, that was the bleaching character data idea, right? That the Broomhead paper you're talking about?
Yeah, I forget now what it was called, but
yeah,
it was something that surprised me at the time, because I was pressing Swinney to just use a bunch of first order filters with different time constants, and I said, why not use that instead of all these delays? And he didn't have a good answer, but then Dave Broomhead came up with this good answer.
Yeah. Yeah, so I believe, and Thomas Jungling, you can correct me if I'm going off base, but I believe that a lot of the effort is in matching, having enough memory and being close enough to being innovative being at the edge of chaos, so you've got innovative dynamics in there.
Yeah, I think that's a fair way to state it.
Yeah. Okay, so but for what we're doing today, I'm going to focus on the more application side of our work. So essentially, each node, each xi, is the state of a node is computed by some combination of the weight matrix, so that's the connectivity of the nodes in your reservoir, some input matrix, which says where you're receiving input from. So the UK is the drive signal, it's the current state of your system, and some offset, which is the standard offset in machine learning, just to make sure that tan H is doing something in the interesting area and not just saturated. And so I'm going to talk about just a couple of ways in which we've kind of applied this idea. And the first, echoing the earlier discussion about the idea of mimicking a dynamical system, and the reservoir in this case as a copy of your dynamical system. So we're interested here in using the reservoir to try to measure and capture the process of onset of generalized synchronization. So if you think of two dynamical systems, X and Y, generalized synchronization with some strength K is going to be, so F and G are the different functions of the different dynamics. So F is working by itself, G has got some other dynamics, but it's also influenced by X. And as we increase K, and on this picture here, where K is increasing from 0.1 up to 30, that doesn't matter what the units are, but we're getting stronger and stronger coupling. So the influence of xt in this coupling function is going to become stronger and stronger. Well, the reservoir, as I wrote it down on the previous page, that's essentially dynamic. If you think of RT as the dynamics of the nodes, then it's essentially some function which is the dynamics of the node plus the drive signal, right? So this R dot equals HR U is essentially your R dot, well, it's a difference equation here, but it's the state of your system as a function of the previous states and your drive signal. So if we're able to construct a reservoir which models the GK, we can measure how well or to what extent the system is in generalized synchronization. And so that's what we're depicting here, is how the model of the reservoir model actually unravels that generalized synchronization and gives us something that we can, well, essentially something we can hang our hat on in terms of measuring how strong that the synchronization is. So the horizontal axis in each of these pictures is my X dot, the vertical axis is my Y dot, what's one component of the input system and the drive system and the response system. At the top line on the left, I'm just comparing those two things, the input to the output, and one would say that there's little correlation, that they're not synchronized. There's no pattern between input and output. As we increase the coupling, there becomes some structure until we get this nice, well-defined chaotic system. But what we're showing on the right is what happens when we try to predict the Y system from the X system. So here in the initial state where it's unsynchronized, there's no effect in that. The X from the Y system. The Y from the Y with, we're trying to predict Y from the previous state of the Y with the drive, because we're reproducing this function here. So we see at the onset of synchronization, the system prediction, and that is when the synchronization kicks in and the reservoir itself is producing an exact copy of the signal that we're driving it with. So treating the reservoir like the dynamical system we're trying to study, we can use that to quantify the strength of the synchronization in that system. Okay, two more little things I want to talk about. The first is an idea which we've been playing with for some time. We still haven't quite got it to work properly, to be honest. But it's just such a nice idea that I'm sure it must work somehow. So the whole point of reservoir is that you've got this idea of memory and you've got this idea of pattern generating. So you're driving your system and you use that drive of your system to generate some interesting collection of patterns. So one of the other things that people in my group, and in particular Shannon, who is the second author on this paper, was working on, was looking at flocking of birds. So she was working on a PhD looking at flocking birds and building models of collective phenomenon there. And we thought, well, why don't we use a flock of agents, so actually boids, not birds, but a flock of agents as a reservoir. So we have a predator, which is shown here in red, and we have a flock of prey agents, which are shown here in blue. The prey agents have some cohesion, so they tend to act as a flock, they tend to follow one another, and we have the drive agent, the one in red, who's moving around chasing them. Except rather than have the drive agent chase them, why not have the drive agent carve out the drive signal in the reservoir sense? So in this example, although you can't see it from these pictures, the red agent, and these are snapshots in time from 0 to 0.9, the red agent is moving according to the trajectory of the Lorentz system, I think. let's call it the Lorentz system, and the blue agents are responding to that and being moved away from it. So we need to carefully balance things so that the blue agents are in the same part of state space as the red agent. But essentially, you've got your drive signal, the red agent, the predator agent's position, and the blue agents are responding to that in some nonlinear fashion. And there's some memory and there's some interaction between them. The essential elements of the reservoir computing paradigm. So we did this, and then we looked at the blue agents, and we tried to build from the blue agents a predictive model of the Lorentz system. And it was appallingly bad. It's probably the worst modeling result that anyone's ever managed to get published in any scientific journal ever. I won't even show you the picture. The prediction was basically flat line, right? We're trying to predict the Lorentz, and we get nothing out of it. So we thought that wasn't so good. But let me show you, this is the same thing visualized over many simulations. So here the blue dots are just one particular flock, but underlying the blue dots is now a density. So it's the density of the average flock over time. Here, the little gray lines are individual trajectories. So it's just showing where the blue dots are going. This is over many 1,000 replicas, 1,000 different simulations of flocks with the same drive signal. This is where over time the agents will end up. So part of the reason we thought that the original system wasn't doing a very good job is that it's just a linear output from the prey agents' positions, right? The prey agents themselves are reacting to the drive signal, so they're delayed behind it, and it's just a linear output from that. So we actually then grabbed the old idea of radial basis functions, and so we've got in the diagram on the left here, we've got our drive signal, which in this case is depicted as Lorentz, and that's the blue agent moving around, sorry, the red agent moving around. The blue agents are responding, moving away from the red one, but staying as a group. But rather than just take a linear output from that reservoir layer, we filter that linear output through a bunch of radial basis functions. The radial basis functions we place according to that distribution of positions. So we're trying to weight it by where we expect the agents to be. So there's a second order problem here in that the agents also are interchangeable. So we lose a lot of information because actually the construction we have, I don't care which blue dot is where, just that there is a blue dot there. That makes sense. So if I have two agents, then agent A and agent B, or agent B and agent A, it's equivalent in the model. So we're trying to grab more information from that. And so this observation layer is essentially a nonlinear filter using radial basis functions that is taking the output positions before feeding it into the linear prediction. And this is probably the second worst prediction that anyone's ever got published in a scientific journal, but at least it's better than the other one. The black line is the truth, and the red line is what the reservoir is doing. So the idea at this point, all it's showing us is that there is some shadow of the dynamics in the agent, in the prey agents, which is not unexpected. There's a high level of creativity there in terms of the dynamics looks quite different from the true one, but we still haven't got anything that could ever be useful as a prediction. What we're working on now, so I hope we're working on now, is better ways to build that observation, to build that output so that we can extract some version of the information that somehow looks nicer. But as I said, it's an idea that's not working yet, but I think the idea of using a flock of agents as a reservoir is just too neat not to be useful somehow. I'm just not quite sure how. Okay, so let me finish by moving back to more practical, more applied problem and some more data from the maintenance domain. So this is an exercise in parameter estimation. So the setting now is dynamical system, x dot equals f of x, but I've got some bifurcation parameter, and I wish to estimate that bifurcation parameter from my time series. So what I'm doing is I generate pieces of time series with different with different bifurcation parameters, and I take each of those bits of time series, drive my reservoir with that piece of time series, and then fit the output of that driven reservoir to give the stationary value of the bifurcation parameter. So on average, the mean value of the output is the bifurcation parameter. So this seems a little bit left field because I've got my dynamics, I'm feeding it into the reservoir, and I'm trying to predict a constant. And that constant, I hope, is the value of the bifurcation parameter that I started with. Why would I even think this was going to work? So if you think about the reservoir as a connected nonlinear system and the activation of the nodes in that reservoir representing the state of my system, as that state changes, different nodes are going to be activated in different ways. And so I would expect, just like if I do a delay embedding, I get different attractors, the way in which the reservoir is activated under different drives from different dynamics will manifest with different outputs. Okay, so that's the hope. And actually, it doesn't work too bad at all. So we've got on the left here, I haven't, this is actually, I've done, well, when I say I, this is a collective I, where what I actually mean is the PhD student at the front here, Braden, he's done it. Braden has looked at the Lorentz system and the Rossler system. So that's these two separate plots here. And in each of these plots, he's comparing from time series, from a model built from different time series to predict different bifurcation parameters, then applied to new representative time series of the same system. He's showing the predicted versus actual value of, well, it's not the bifurcation parameter because it's been scaled, but it's a, well, actually, it is a bifurcation parameter. Well, he's showing values of the bifurcation parameter versus the predicted bifurcation parameter with 5 different learning regimes. So the reservoir computer is the echo state network shown here. There's a spectral filtering construction here. There's 2 different machine learning paradigms here. One is in the spectral domain, one in the time domain, and there's a linear model built from a delay embedding up here, with V1 and V3 being 2 different versions of that delay embedding. So apart from the delay embedding, what it's showing is that actually it doesn't work too badly at all. And the reason for this is that I've trained the model with sections of time series under particular domains. And when my testing data is a new piece of time series, but it's under the same dynamical regime, right? So although it's a new set of data, it's new observations, it's still behaving in the same way. And so the model fit is actually working quite well. It's predicting, I can drive the machine with a section of time series, and it can tell me what the bifurcation parameter should be for that piece of time series, for the Rossler and for the Lorentz system. Yep. Right, so here you don't have the same problem with the delay embedding with the Rossler system. I believe, and Thomas or Braden will correct me if I'm wrong, I think the issue with the delay embedding method here was to do with the 2 lobes of the Lorentz system, but I'm not sure. So finally, we then take that to the real world, and you can tell this is the real world because with the Lorentz and the Rossler system, I got nice, beautiful straight lines. It's almost on the identity line, my prediction versus my truth. This is the real world data. So this data it's an experiment that was done with industrial pumps. So a large amount of the problems that our industrial partners in this training center are working on is processing plants that involve pumping messy goop around some facility. And it tends to be nasty, viscous, toxic stuff. And so they have these big industrial pumps to make this work. These pumps clog, they break down, they need to be repaired. If you repair them, you have to switch them off and replace them, and stuff stops working and they stop making money, and they don't like that. The interesting thing for us is that as these pumps proceed from normal operation to failure, there's a process of cavitation, right? So Melinda, I don't think is here, so she won't be able to correct me, but to me, I naively think of cavitation as to what a water pump does when there's air in it and it starts to make noise. Melinda tells me it's a bit more complicated than that, but essentially the pump begins to break down in terms of its capability to pump the fluid. They can measure this, except measuring this is complicated and involves expensive sensors going into the system to measure it. When they do measure it, they call it either NPSH margin ratio. Unless anyone here is a industrial engineer, it doesn't matter what that is. It's some property of the pump goodness of behavior, or it's called cavitation number. So there's two sets of pictures here. This is for NPSH margin ratio, and this is for cavitation number. And again, each of these pictures, I've got the true value of these things as measured on the pump versus what I've got out of my prediction algorithm from each of the schemes that I've employed. All right. And I think Braden's rather optimistically fitted straight line. I think the straight line here is what we'd expect for the identity. And excuse me, first glance, one would say these look pretty terrible. But actually, it's not terrible at all. It's pretty good because mostly it goes up when it goes up. So when the truth goes up, the extracted value goes up. And in terms of getting an indicator of failure of these machines, that's all they want. They really just want to see that if we're taking successive bits of signal from it, if the values are progressively going up, then the prediction that we get progressively going up is telling us that the pump is closer to its critical failure regime. A little bit disappointing for the reservoir computer here, although this result is not too bad. I've become increasingly optimistic looking at these pictures. This plot's not too bad. It does go up. I would say these other ones do a better job of it. Nonetheless, the idea of estimating the parameters here works, even if the reservoir computer isn't the best performer out of those three possibilities. Anyway, that was my last example. I just wanted to show some applications of where we can actually attempt to use these sorts of stuff. The nice thing here, of course, is that actually the delay embedding, even as a linear model, is not performing too badly. That's the last example I want to show. The general take-home message is that whether we're looking at reservoir computers or we're looking at radial basis functions, whether we're using reservoir computers with Tikhonov regularization and all the modern fancy ways of people doing ridge regression, lasso optimization, all that stuff, or whether, and compressive sensing, or whether we're looking at mem description length, the basic idea is that you're just fitting a surface. Your model itself is somehow encapsulating a sequence of history, either through the memory of the reservoir or through the delay embedding of Tarkins and co. And the sort of predictions that we can get out of these models are actually, even in some fairly challenging settings, and predicting cavitation in industrial pumps is not easy. Even in some fairly challenging settings, you can get results that are fairly reasonably behaved. I will stop there. I've got, as is traditional, a long list of references. I would just point out that at the bottom of this, the description length radial basis code, which I described and showed in those earlier results, that code was implemented 20 odd years ago in MATLAB. Ran on a machine that has less memory than my phone. I've re-implemented all of that in Julia, and the difference is chalk and cheese. It still works, as far as I can see, better than any of the competitive packages. It's a bit researchy because I've just written it for myself, so there's no warranty attached to it, but have a look at it by all means. And the more recent work, mainly work of Thomas Limburn, who was in the audience earlier, if he hasn't got bored and gone home, He's just finished his PhD here at UWA. Thomas Jungling, who was supervising him. Braden Thorne is starting his PhD looking at the industrial maintenance project. And Melinda was helping me out. She's the resident engineer in that group. Thank you very much for your attention.
Thank you very much. Thank you. Any questions, comments?
Thanks, Robert. Any other questions?
It seems there are no other questions. I had questions about the estimating the parameters of the bifurcation parameter from time series.
Yep.
So do you think that this would work for other systems in general, or that seems like kind of?
So, and Thomas, tell me if I'm wrong here, but I think it's working here because we are building a model on types of dynamics we've seen. And when we see the same type of dynamics again, albeit different trajectories, we can estimate the bifurcation parameter. It's only going to work, well, we haven't really looked at how well it interpolates to values of the bifurcation parameter that we didn't see in the model building. Is that right, Thomas?
Yes, we didn't look for extrapolation or not too extensive.
Yeah, so it will work, but it works because it's building a model on behavior that you've seen to predict the corresponding, and predict's probably not the right word, predict the corresponding value of the bifurcation parameter. A long time ago, I tried to do something like this with extrapolation. Of course, it gets very hard. It's very, very, very difficult to make any sense of it. But I think that these techniques, there is promise that they can do more than what we're doing at the moment.
Yeah, I was wondering.
The only thing that I would add to that is it's a bit hard to predict what they're going to do because, for instance, in the synthetic systems we saw, we had models in the time domain and models in the spectral domain. The synthetic systems, the models in the temporal domain performed better, but for the real world data of the pumps, the models in the spectral domain performed better because apparently the change in parameter was more indicated in the spectrum rather than in the temporal structures, but depends from case to case, needs to be tried out.
Yeah, it depends on exactly what you're trying to estimate, right? So with bifurcation parameters of dynamical systems, it's well understood how your bifurcation parameter is affecting the degree of periodicity of your system and all that sort of stuff. Whereas with these systems, well, unless you're a mechanical engineer and really understands what's going on, it's not clear whether temporal domain or spectral domain is the right place to look. Although I guess I would say that engineers are always looking at the Fourier domain. So,
I was thinking from, for example, like how bifurcation, like would you be able to detect the the critical point?
Yeah, I believe so.
Yeah. All right. Okay, thank you. Any other questions, comments? Yeah, all right. So it seems that there is no further questions or comments. Okay, thanks a lot again for the nice talk.
Okay, thank you. Thank you for having me.
Yeah, thank you very much. Yeah, thank you everyone for coming. Thank you. Bye-bye. Take care.
Enjoy the rest of your day or your evening, depending on where you are.
You too. Yeah, thanks. Bye-bye. Thanks.
Thank you.
Thanks. Bye-bye.